So this talk is based on two works. One is with Mathieu Alfaro and Pierre Gabriel from Université of Versailles, Paris Saclay. And the other one is a work published some time ago about the Fokker-Planck equation with my friend Stéphane Michler and a student of us, Mamadou Ndao. So, by the way, maybe I have written many things on my document. This is because I can give it to you in order to have some documents for later on. So you don't need to take notes if you if you want to notice some particular aspects of the equation of the problems. Okay, so the kind of problems we are going to treat here is the following. Take a Banach space X, which is a subset of L1, or a subspace of the space of measures, okay? And consider a semigroup which acts on this space. So I recall that for young students or post-graduation students, we call a C0 semigroup on X a family of bounded operators such that S of 0 is identity and you have the semi-group property. And the continuity means that as t goes to 0, S of tu converges to u. Moreover, we assume that the semigroup which is considered is positivity preserving. This means that if the initial data is positive, then S of t applied to F remains positive, okay? And we want to know what happens to S of t applied to F whenever F is a positive initial data, okay? So there are various situations. One of them is when S of Tf converges to 0 as t goes to infinity. So we want to know the speed at which S of Tf converges to 0. In other situations, it happens that we know a non-trivial equilibrium which is positive and non-zero, of course, and we want to know S of Tf converges to this equilibrium at a certain speed, okay? So both situations, in fact, appear in application, so we want to understand this problem. So a first example is the following. We consider an evolution equation for which we have a linear part, which is given by a convolution J star F minus F. This part is linear, and here we have a weakly nonlinear term, which is here. In fact, this term it's important in the application, but not very much in the study we are going to undergo here. And we want to solve the equation for the total mass of the initial data equal to 1, and everything is set up in such a way that the integral of f of t remains equal to 1, okay? So this is again for applications, okay? So the difficulty here is that the part which is linear sigma squared J convolution F minus F is a non-local operator, and so it is not easy to understand how one can find an equilibrium for this equation. Okay. So once we have this equation, there are several ways in order to find the equilibrium. One way is to show that 0 is a point of the spectrum of L and it is an eigenvalue. So this means that you can find a function phi such that L of phi is equal to 0. Once you have L of phi equals to 0, then exponential of TL, the semigroup applied to phis, is equal always to phi. Then we, in order to prove the decay of a positive solution of the evolution equation to this equilibrium, we need to show that there is some gap between the eigenvalue 0 and the remainder of the spectrum. If this can be done, then we can show that the convergence to the equilibrium is exponential in time. Okay, so this is so although the result I'm going to show here is not exactly what I'm going to use, but the proof I'm going to show you is a proof by Wolfgang Döblin, who was a young German mathematician who flew to France in 1940, and he was against the German at that time. So before going to the war, he wrote some mathematical notes and he sent to the Académie des Sciences in Paris, and his notes were unsealed only in 2000, after 60 years. So this was the requirement for him to be published only after 60 years. Unfortunately, he died in May 1940 when the Germans attacked France. But the proof is one of the most beautiful proofs I have seen in mathematics, and I cannot resist whenever I talk about convergence of to equilibrium for evolution equation to show this result. So assume that you have a semigroup S of t which acts in the space L1, and it conserves the mass of the function. So m of f means the integral of f d mu. So for some measure or some, assume that is in Rn, it doesn't matter what the measure is. So you have a semigroup which conserves the positivity of initial data, and also it conserves the mass of the function. So the result is the following. So the result you see is quite simple. It says that assume that you can find a time capital T positive and a number theta between 0 and 1, and a function phi which is positive. Phi is going to be in fact sort of the equilibrium for the semigroup, okay? And assume that the semigroup applied to a function g verifies S of tg larger than theta times something phi, okay? So this means that you have a function phi and the number theta which is below any positive solution of the evolution equation after some time, okay? So this means that you begin with anything which is positive somewhere, but at the time capital T, which is uniform for all initial data, the solution goes above something, okay? So now the result is, if you take a function f which is in L1 and mean value equal to 0, then S of capital TF is less than 1 minus theta F. Of course, you see that if you apply several times this means that F of NT times F is less than 1 minus theta to the power N. So it goes to 0. Okay. So the mere estimate from below, which is in equation 2, tells you that all functions which have mean value equal to 0 converge to 0 exponentially. Okay. So the proof is that if you assume that M of F is equal to 0, then writing F as its positive part and minus negative part, this means that the mean value of F plus and F minus are the same. So we call this number lambda. Then S of capital TF in norm L1 can be written in this way just by adding and subtracting this term theta lambda phi, which is lambda is this number and theta and phi are the number given before. So, okay, so theta is this function, this number, and phi is this function, which is below anything. Okay, so now we apply the triangular inequality. So we have inequality 5. And since we know that S of T applied to F plus minus theta lambda phi is positive, this means that this norm is in fact integral of the function, which is because it is positive. Okay. But now, if you compute this integral is precisely 1 minus theta lambda. So you plug this number here, you find that S of T F is less than twice 1 minus theta lambda, and this is precisely 1 minus theta norm of F in L1. So end of the proof. Okay, you see the proof is just a few lines. But now from this, it is easy to conclude that the convergence of the S of Tf for any function f which has mean value equal to 0 is exponential. So it's less than 1 minus theta to the power n. Okay. So this is a very, very powerful method. But in order to apply this, we need to find an equilibrium phi, which is positive, and any other solution of the evolution equation might be comparable to this equilibrium. Okay, and in most applications, this is the difficult part. You can so this is so if it were, for instance, for a parabolic equation, this would be sort of strong maximum principle for the parabolic equation. Okay. Nevertheless, one can use the ideas behind the proof of Dublin's theorem in order to prove exponential decay. So the idea is to find at capital time t such that after this time, any initial data is transformed to something which is above the equilibrium. Okay. So now I would like to go back to the examples for which we want to show the existence of a ground state. So the equation we consider is the following. So again, we have the equation we saw before, which is a non-local equation. And we want to find an equilibrium. So this means that dTF must be equal to 0. If dTF is equal to 0, and F0 is the equilibrium, then this part, which is written here, must be equal to 0. Okay? But now this part is something which is weakly nonlinear in F, but by calling this number lambda, we end up with an equation which is like this. So this is a sort of eigenvalue problem. You see, on the left-hand side, you have minus sigma squared J convolution with F0 plus W times F0. This must be equal to lambda minus sigma squared F0. So lambda minus sigma squared is going to be an eigenvalue, and F0 is going to be the eigenfunction, okay? But now the problem is that, okay, we want to find an eigenfunction as in equation 7, and therefore, since J is assumed is a kernel of which is in L1 and in L2, and we assume that it is symmetric. So J of minus X is equal to J of X. So this means that the operator, which is here, minus sigma squared J convolution F, is a self-adjoint operator, okay? So the problem is to prove that this operator has an eigenvalue lambda 1, and in order for this eigenfunction to be of use in the evolution equation, we must show that lambda 1 is larger than the number minus sigma squared. Okay, so this is what. So here are the assumptions on J. J is an even function. Integral of J is equal to 1. And we assume that J is strictly positive, larger than J0 positive, on a small ball near the origin. Okay. And the potential W is assumed to be coercive, which means which goes to infinity at infinity, and W is positive. And moreover, this condition 11 is very important. It is almost necessary in order to have the eigenvalue. So we assume that at some point where W is equal to 0, the function 1 over W is not in L1. This means that the function W vanishes at its minimum sufficiently fast such that 1 over W is not integrable. Okay, so this is an important requirement for the equation, for the operator to have an eigenvalue. Okay. Okay. Equations such as the one we are studying have been studied by a certain number of authors, but essentially for operators which look as the kernel of the minus Laplacian to the power s. Okay, for s between 0 and 1. But in order to see what are the differences between what we know for the partial differential equation and a non-local equation as the one we have here, assume that you have this equation. So the linear part is replaced by Laplacian of f. W is this function x squared minus x to the 4 minus x squared. So we want to find an eigenvalue of this. In fact, for this in any dimension, as soon as the potential goes to infinity, it has been widely studied for instance, in the book by Reid and Simon. You have many examples, and also Tartayan, who have studied various conditions on the function W, so that there exists an eigenvalue λ1 and a positive function, which is called the ground state. Okay. But as we are going to see, in our case, the difficulty comes from the fact that we have this operator, which is sigma squared j convolution f minus f. And this operator has a domain which is not locally compact in any space, as we are going to see. So this is the main result. There exists a function phi which is continuous, which goes to 0 at infinity, and we have an eigenvalue. Okay, so λ1 such that we have this this equation, and λ1 is between 0 and minus sigma squared, and phi of x is less than some constant over w of x. So this means that if, for instance, w of x converges to 0 as if w of x converges to plus infinity as x to the power 4, then phi converges at least as 1 over x to the power 4. Okay. So it is natural to, since we have a self-adjoint operator, it is natural to use a variational method in order to find an eigenvalue for this operator L. So we define the energy functional E of u, which is LUU, so, which is minus sigma squared integral of JU times u plus W integral of W squared. And we are going to find a critical point of this functional on the manifold, which is essentially the sphere of L2, but U belongs to the domain of the operator L. This means that 1 plus W in integral of 1 plus W squared is finite. Okay. So if we prove that λ1, which is the infimum of the energy on the manifold S, if we show that λ1 is achieved and it is achieved at some function phi which is positive, then we are done. We have the eigenvalue and the eigenfunction. Okay. But the problem is that, as you see, if you have a sequence which is weakly convergent in S, okay, since you don't have any information on the norm of the gradient of this sequence, there is no way to use a compactness result, okay? Because you see the only condition we have is that U belongs to L2 of 1 plus W. L2 of 1 plus W is contained in L2, but of course there is no compactness, no local compactness, no of any kind. Okay, so the difficulty comes from here. So in order to show that we have a this λ1, which is defined as the infimum, is achieved, the first step, which is the crucial step, in fact, is to show that we can find a function u in S such that the energy is negative, and therefore the number λ1 is negative. Okay, once we know that λ1 is negative, we can show that in fact λ1 is achieved. First, one shows that if un converges to u weakly in L2, then the quadratic term where the convolution with J appears converges to what you want. The reason for this is essentially the fact that, you see, if U UN is in L2, J is also in L2. Therefore, J convolution with UN, in fact, is in the space of C0, continuous function which go to 0 at infinity. And using these facts, one ends up to show that the convergence here holds. Okay, so whenever UN converges weakly in L2, then this integral of J convolution with UN converges to what it must have. Okay. So this is the second step. The third step is to consider a minimizing sequence. But since the energy doesn't change when you, or doesn't change, or it decreases when you replace U by its absolute value, then we can choose a minimizing sequence which is also positive. So we have a sequence phi n in S, phi n positive, and E of phi n is between lambda 1 and lambda 1 plus 1 over n. Okay. In particular, for n large enough, you see that the energy of phi n is going to be negative. Okay. Now, we have that the integral of W phi n squared is equal to the energy of phi n plus this convolution part. Okay, but now we know that this is bounded because norm of phi n in L2 is bounded, so this one is bounded by 1, this integral, and E of phi n is less than 1. So all this is less than lambda 1 plus sigma squared. Okay. So now, if we assume that phi n converges weakly to phi, so phi n is bounded in L2 of 1 plus W, therefore we can assume that phi n converges weakly to phi. Now, by using Fatou's lemma, you see that the integral of W phi squared is less than lambda 1 plus this integral, and this is less than lambda 1 plus sigma squared. Okay. But now, if we remember that lambda 1 is negative, okay, this implies that phi cannot be equal to 0. Okay, because if phi is equal to 0, you see that integral of W phi squared is 0. Here you have lambda 1, which is strictly negative, and here you have sigma squared, something 0. And this is not possible. So this inequality, in fact, implies that phi is not equal to 0. Okay, so we have just from a weak convergence, we have concluded that phi is not 0, the weak limit is not equal to 0, because the energy lambda 1 is strictly negative. And moreover, the same inequality shows that lambda 1 plus sigma squared is strictly positive. Okay, so this is the third inequality which is here. The third term of the inequality which is here. Okay. Now, what we know is that the energy of phi is less than lambda 1, and the integral of phi squared is less than 1. Okay. Now assume that theta, which is the norm of phi in L2, is strictly less than 1. Therefore, if we consider phi tilde, which is equal to phi divided by theta, then phi tilde belongs to S, and we have lambda 1, which is less than the energy of phi tilde, but the energy of phi tilde is a quadratic functional. So this means theta to the power minus 2, and E of phi is less than lambda 1. So we have lambda 1 less than theta to the power minus 2 lambda 1. But since lambda 1 is negative and theta is less than 1, so we have this inequality, theta to the power minus 2, lambda 1 is strictly less than lambda 1, so there is a contradiction. Okay? So this means that we must have theta equal to 1, that is, phi, the norm of phi is equal to 1. Phi belongs to S, excuse me. And the energy of phi must be equal to 1. And finally, using the equation, one sees that phi is equal to sigma squared J convolution with phi, and therefore phi belongs to C0 of Rn. Okay, so this is the end of story. Okay. So now this is about the existence of a ground state for the non-local equation. Okay. Now, if we want to show that the solution of the evolution equation, or at least the linear equation, converges to this equilibrium, we need to show a spectral gap. Okay. So once we have this the spectrum, the function, the eigenfunction phi, which is positive, so now we can find the second eigenvalue of our linear operator. And in order to do that, we consider the constraint S0, which is the set of U which are in L2, U scalar phi is equal to 0, and integral of U squared is equal to 1. Okay. And now we consider lambda 2. Okay. So now the result is the following. We have either lambda 2 positive or 0. Okay. In this case, we have the gap, which is lambda 1 strictly negative and lambda 2 positive. Okay. So therefore, we have the gap between lambda 2 and lambda 1. The spectrum of L is going to be above lambda 2 for the orthogonal of the function phi. And if lambda 2 is strictly negative, then it is achieved. This means that if lambda 2 is negative, we have a second eigenfunction. Okay. And in this case, we have to show that the eigenfunction, the eigenvalue lambda 1 is simple, and therefore we have a strict inequality. Okay, so this can be done exactly in the same, more or less the same way. We have to show that lambda 1 is simple, but this is based on a sort of maximum principle, which has to be shown for this case. But what I would like to show is this the method for another the method to show existence of an eigenfunction for another type of equation for which there is no variational method. Okay, so this is the Fokker-Planck equation. So the Fokker-Planck equation is sort of heat equation, except for the fact that the linear part is Laplacian of f, which is the self-adjoint part, and we have a non-self-adjoint part, which is divergence of f times E. What is E? E is a potential, a field force, which may be from a potential, but it is not necessary, such that x times E of x is larger than x to the power gamma, and the gradient of E is bounded by something x to the power gamma minus 2. So essentially, E of x is something, a force field which behaves like norm of x to the power gamma minus 1. And gamma can be between 0 and 2. Okay. In fact, it is easier to study the problem when gamma is between 1 and 2. And when gamma is between 0 and 1, the situation more complex. And what we are going to consider here is the case when gamma is between 0 and 1. So a typical example of a function E is when we have E of x, which is the gradient of a potential, and assume that the potential is 1 over gamma norm of x to the power gamma. Okay, so this is something very common. But in fact, one can consider other types of potential. Assume that V is in C2, and we have the equation which can be written in this way. If the equation is written in this way, then we can write the equation as something which is dt of f equals to e to the power minus v divergence of ev gradient of f plus Laplacian of v phi. And now this operator becomes a self-adjoint operator in the weighted space L2 of e to the v dx. Okay, and then according to the behavior of the function v, it is more or less easy to show that there is the first eigenvalue and a positive eigenfunction, etc. Okay. So a typical example again is this case, for which you can compute explicitly the eigenfunction, which is the exponential of minus x to the power gamma over gamma. Okay, and once this is done, one can show that the solution of the Fokker-Planck equation converges to a multiple of this eigenfunction. Okay, but when the force field E is not the gradient of a function, then there is no variational approach in order to show the existence of an eigenfunction, a ground state. Okay, so this is what I would like to show. Here there are some assumption and notation, so these are not important. I want just to show how we can tackle the problem. Okay, so we consider the operator L, which is Laplacian of f plus divergence of fe, and the domain of L is is as usual the function phi, which are in the Sobolev space, and L phi belongs to L2. The index k means that instead of the Lebesgue measure, we may consider other polynomial weights. Okay. First, one shows that this operator is the generator of a C0 semigroup, but there is no decay. Okay, one can find a certain number omega which is positive, such that the norm of the semigroup is like exponential of omega t. So it may have an exponential growth, not a decay. Okay, but nevertheless, we can show that if one chooses the weight correctly, then in the space with that weight, we can find an eigenfunction, which is Laplacian of G plus divergence of GE equals to 0. And the solution of the evolution equation converges to this. Okay, so this is what I want to show. So first of all, we show that by using some splitting of the semigroup SL, this means the semigroup generated by L, and also is a splitting of the operator L in two parts. One part is where the field force has a compact support, and a part which is at infinity. By mixing these two things, which is quite technical, we can end up by showing that the semigroup SL, in fact, is bounded from LP into LP. But before doing the splitting, which I don't have time to detail, we had only an exponential growth. Okay, we had exponential of omega t. But now, once this is done, we can show the existence of the semigroup. Okay. First of all, we choose a measure which is very strong. Okay, and we are going to find an eigenfunction in this space, the space L2 of this weight, which is exponential growth. Okay. First of all, since we know that we can show that the semigroup is bounded in this space by using an integration by parts, it is not difficult to show that when f is positive, when the initial data f0 is positive, f of t remains positive, and the integral of f remains equal to the integral of the initial data. Okay, so this is just by integration by parts. This is not difficult. Now we use a new norm on the space L2, which is with triple bars, which is the supremum of SL of t applied to F0 for all t positive. Since we know that SL of t is bounded, so this is always well defined. Okay, and one can show that this norm is the space L2 of M0 with this norm is a Banach space, etc. Everything is as usual. And now with this norm, SL of t becomes a semigroup of contraction. This means that the norm of SL of t is equal to 1, or less than 1, excuse me, less than or equal to 1. Okay. Now consider the convex set, which is the set of function f which are in L2. F is positive. Norm of the triple norm of f is less than r, and its mean value or its integral is equal to 1. Okay. Now it is clear that if you choose r large enough, then this set K is not empty. Okay, and of course it is convex and closed, because everything is continuous. Okay, so we have a closed convex set K, which is not non-empty, and it is conserved by the semigroup SL of T. Okay, because the first condition positivity remains positive. Since SL of this contraction, the ball of radius R remains the same, and the mean the M of F equal to 1 remains M of M. The integral of the solution is equal to the integral of initial data. Therefore, we have SL of T, which is a semigroup of continuous linear operators on a closed, weakly compact convex set. Okay. And thanks to the theorem of Markov-Kakutani, there is a fixed point which is common to all the family of SL of T. Okay. So the theorem by Markov-Kakutani is done exactly for the study of equilibrium for semigroups, in fact. Okay. And in fact, it is in a framework of topological vector spaces, locally convex, etc. So here we are in an easier case because we are in a Hilbert space. Okay. Therefore, we have a fixed point of all the semigroup. And of course, if SL of TG is equal to SL of TG is equal to G, this means that LG must be equal to 0. First, since this is equal to G, this means that G belongs to the domain of L, because the derivative of SL of T, G is equal to 0, and LG is equal to 0. And then using classical techniques of maximum principle, one shows that G is positive. Okay. And then one has to show that in fact, because here the operator L is not self-adjoint. Therefore, we have to show that the kernel of L is exactly of dimension 1. This means that N of L is the span of this eigenfunction. And we have also to show that the spectrum of L, except 0, is contained in a half space far from 0. So this means that sigma of L minus 0 is contained in the half plane real of Z, Z less than minus omega star. Okay. And once this is done, so we have the spectral gap, and then one has to show the convergence to the equilibrium. Okay. So I think my time is almost finished. So I can stop here.